Good afternoon, everyone. Please join me in welcoming Michael Droettboom and Dino Viehland for Going Faster in All Direction, how two teams are working together to make Python better for all.
Hi, good afternoon. So we are going to talk about going faster in all directions at once from two teams. Well, first, what are the two teams? So there's the faster CPython team that is mostly responsible for these two PEPs, the specializing adaptive interpreter and optimizing Python's execution, or otherwise known as a JIT. And the people on that team are Mark Shannon, who wrote his PhD thesis on quickening Python and other things, Brant Bucher, Eric Catriel. She is responsible for the idea for this talk, so if you don't like the talk, take it up with her. Eric Snow, who's up here in the front row, myself. You may have heard of Guido van Rossum. He was on our team until a few months ago. And as well as some people who are not at Microsoft, Ken Jin and Savannah Bailey, both also like super big contributors. You have probably heard that there's a change in funding. We're really grateful that we got almost 4 years of funding from Microsoft to work on this. We're not really sure what the future holds, but we do want to keep it going in some form. We're figuring that out. And then I'll pass it to Dino.
Yeah, so I'm Dino Viehland, and I work at Meta. The Meta team, Sam Gross started Faster CPython, I think almost 4 years now ago. So it's been something that has been a passion project of his for a long time, and he's done an amazing amount of hard work to figure out all of the pieces that need to come together to actually make this work. Matt Page has been working on it. I myself has been working on it. Thomas Wouters has been working on it. And there have been several people who are no longer at Meta, and also lots of people in the community who have contributed to make this a reality.
And so when I talk about two directions at once, basically that first effort of faster CPython is trying to make single-threaded performance of Python faster. So if you're just running code in a single thread, making that go faster. And of course, the free threading team is working to scale that out in the other direction and have as many cores getting utilized as much as possible and get speed in that way. And we are doing this while Python already exists and trying to insert this new functionality into it without tearing it down and wrecking it for the whole community, which adds a whole other layer of difficulty. So we're going to sort of talk through the technical aspects of both of these a little bit and then try to bring them together and talk about why they are sometimes a challenge to work together and how we've worked through that as well and made both projects successful. So a very quick introduction to the specialized adaptive interpreter here. On the left, I have some example Python code, and Python is converted to bytecode, which the interpreter then runs through. These two lines that I've highlighted are represented by this bytecode. You're basically taking some values off of the stack, performing a binary operation on them, and then putting the result back on the stack. And this binary op bytecode, because Python is a dynamic language, it basically has to go, what are the types of these objects, figure out what operation is actually the appropriate operation to perform on those objects, and you do that every single time you do that. You're starting from zero knowledge about what the objects actually are. So the specializing adaptive interpreter is able to notice that every time we come back to this, they always seem to be integers. So let's replace that bytecode with one that's specialized just for integers. And obviously that's a whole lot faster because it doesn't have to do all of the checking what it is before it can do the operation. And so beyond that all of that was kind of the first version that shipped in Python 3.11. Beyond that, we now have a just-in-time compiler and sort of a tier 2 interpretation where we take those bytecodes, and for each of them, we replace them with a set of micro opcodes. In fact, the bytecodes are now defined in terms of what micro opcodes make them up. So it's very easy to then have the interpreter replace each bytecode with the appropriate micro opcodes. Each of the bytecodes here in bold has micro opcodes, but I'm only showing a couple of them here just to make the slide manageable. And you see here now the binary op multiply int opcode gets replaced with a guard to check that the left-hand side is still an integer and the right-hand side is still an integer, and then the actual operation. And what you can do once you've done this is you can start to perform optimizations that remove some of these micro opcodes because now they're redundant. So in this particular case, which is meant to be super simple, it actually gets a lot more complicated, but we know that the left-hand side and the right-hand side are the same object, so there's no reason to check both times that they're integers. And then we know that the result of the multiplication here, since it's always integers, since the inputs are always integers, the output will always be an integer, and therefore we can remove a guard with a subsequent operation because we know it is guaranteed to also remain an integer. So there's a whole stack of optimizations of that form and of other forms that now we can do with micro-ops that we couldn't do when the operations were higher level. So now I'm going to pass it to Dino.
All right, so what is the global interpreter lock? This is one big lock that basically makes sure that only one thread is executing Python code at a time or running inside of the Python runtime. It greatly simplifies the memory management in Python because you just don't have to worry about data races at all. One of the most significant things it does performance-wise is it makes sure that you don't have to deal with races during reference counts. If you had to take a lock every time you're just bumping a number or decrementing a number, that would slow things down a lot. And this is part of the reason why many people have tried to remove the global interpreter lock, but no one has been successful quite yet. So we're removing the GIL because it protects all of the shared state and makes your programs not scale. And in order to do that, we need to manage that contention in some way. And so there's a few different things that we're actually doing. The first is biased reference counting, and so this lets most reference count operations proceed without any contention. We're also optimistically avoiding locking on containers, and that's a really interesting set of lock-free algorithms and really leans heavily on some thread-safe memory management stuff, which is kind of super interesting. So biased reference counting is one of the first things that we are doing. And so in the GIL builds, you have a simple ref count field in every single object. That gets incremented or decremented. But in the no-GIL builds, things are a little bit more complicated. So we have that each object has a thread ID, which owns it. And that thread ID can freely increment or decrement this local reference count. So there's no sort of atomic operations required there. It's really basically the same thing as incrementing the old OB ref count. But there's also this OB ref shared, and this will require an atomic operation to actually bump the reference count. So if you're accessing an object that was created on one thread from another thread, it's going to be a little bit slower. Then we want to have no contention on all of the core data structures that you use in Python, like lists and dicts. If we had to take a lock every time you read something from a list or a dictionary, it's not that the locking itself is slow, but when there's actually contention on that lock, the threads need to block, and that really slows things down quite a lot. So dictionaries are used all over the place that are particularly shared across threads. So if you think about sys.modules, you think about your globals, you think about built-ins. If we had a lock every single time we read these things, you just wouldn't scale at all. There's other data structures that still just use these simple locks. Set, dec. I think there's some work on set to improve it, actually, but I'm not 100% sure where it's at. But if you modify these data structures, they'll still lock. The lock-free reads are just able to tolerate those mutations while they're in flight. There's a lot of complicated memory management stuff that makes this all work. There's QSBR, where we actually free memory for real when the program is at a known safe state. And the way this works is we may have like something like a list that's resizing, and we're done with the old array, and we know like we're at point X in time. And when all of the other threads have gotten past point X is when that memory will actually be freed. So we just enqueue the free, and it happens later. We've replaced the allocator with the memalloc allocator. It's a thread-safe, largely lock-free allocator, so we don't have to worry about the guild protecting the allocator state. And there's this really interesting detail where objects really have the ref count that's laid out at different locations in memory from the start of the object. And so we have different pools of objects, and I'll get into why this is important on the next slide. So that sounded like a bunch of mumbo jumbo probably. But let's walk through what a lock-free read from something like a list looks like. So here I have an array of memory. It's a bunch of Pi objects. It's in a list, let's say. So each Pi object points to the object header. So we have that ref count information that we saw before. And I want to pull this object out and know that I've safely done so. If the object is owned by the current thread, it's easy. No one can be freeing that object behind my back. So I can just bump the local ref count, I can return the object, we're done. Life is nice. But if the object is not owned by the current thread, someone could be trying to remove this thing from the list at the same time, and so I need to deal with the shared reference count. This reference count could be 0, though, and the owning thread could be like, oh, no one owns it. I'm just looking at my local reference count. I'm done with this object. So we actually need to make sure that it's shared already. And if it's not shared already, we have to lock the object and then go through the special dance to make sure that the owning thread isn't freeing it behind our back. If we've gone through all of that, we've bumped the shared reference count, there's one final check we need to do. We need to make sure the object's still there. If it's not there, we're actually going to decref it. And this is where that object layout and having the reference count be at the same location really matters. If we were accessing something that wasn't actually the reference count, we may have just changed the type object to be +1 temporarily, and we would crash on it when we're reading it later. And that would give us a bad time. So as long as the object's still there, we've successfully, or if the object isn't there, we failed to incref it, now we just decref it again. We changed some random object, but we just moved it and moved it back, so everything's fine. So there's a lot of things that need to be protected, and there's the first class of things is kind of the things that you think of as your program. So these are globals and built-ins, these are types, these are objects. Really, it's all just objects, but that would be a very simple slide, so that would be kind of boring. There's also a lot of things that you probably don't think of, and this is the mutable interpreter state that all needs to be protected. There's the bytecode, and previously this wasn't a big deal, but as Mike talked about earlier, we are now mutating the bytecode. So this is something that needs to be protected. The bytecode has various inline caches. We need to deal with thread safety there. There's also this thing where types have versions. So every time you mutate a type, it gets a new version number. And these versions are used in inline caches, the inline caches that the faster CPython type team has added. And they were traditionally used in this type cache, which also needs to be thread safe. One of the interesting things about these is you change a base class, all of your subclasses have new type versions as well. So that needs to be kind of a big atomic operation that happens. There's also these shared key dictionaries that you may or may not know about. So if you have an instance of a class, all of those instances share the same keys, actually. And this is, again, more mutable hidden state that you may not be aware of. This used to be somewhat simpler, but as part of the optimizations that the faster CPython team has done, they've added these inline dictionaries. So instead of actually having a dictionary exist for your object, all the attributes can be stored in that object itself, and the object references these shared keys. So this is great for memory efficiency in your programs, but adds sort of all sorts of interesting state changes that need to happen in a thread-safe way. So how do we make this all work? With globals and built-ins, these are dictionaries. There's 2 of them. You look up in both of them to resolve any global variable. And so that actually needs to happen in a way where we can lock both objects at the same time. And then once we've done that, we can cache the dictionary versions and proceed with lock-free reads inside of the quickening interpreter. For the type mutations, there's actually just one big lock. So it's no longer a global interpreter lock, but it's a global type lock. It lets us invalidate all of the class hierarchies at a single time. When we are updating things like the attribute cache, we just take the type lock, and then we can cache the type version, and that invalidation happens in a thread-safe way. So back to the specializing adaptive interpreter.
So yeah, this slide is just, we're coming back to one we saw before, basically as a reminder of we are mutating the bytecode, right, in order to make specialization work. And the solution to this, to make this compatible and thread safe to work with free threading, was basically some work that Matt Page did, where we now have a copy of the bytecode for each thread, and each thread will specialize in its own way. It eliminates any need for like locking when you're mutating the bytecode, obviously, which is a whole lot faster. And we do a special thing too, where the specialized code kind of does stay around, so it can be reused after thread exits, which is another sort of important optimization. And I think you were going to talk to the rest of this.
Yeah, so the other big thing is when we read attributes from instances, we want all of that to be lock-free as well. This is kind of just a variation on our lock-free dictionary access, because like previously, attributes were stored in dictionaries. Now we need to deal with the inline dictionaries and all of those transitions, but reading from the inline dictionaries themselves is really simpler, because it's actually just like reading from a list. So that's kind of nice. This is a graph in particular, about the bytecode optimizations, and it shows really kind of how important the specializing interpreter is to CPython's performance now. So we started off disabling the specializing interpreter because it was such a hard part to get thread safe before we did those multiple copies of the bytecode. And so at that point in time, the performance was like 0.7 compared to the build with the GIL. And as Matt worked on getting more and more of the specializing opcodes working, after he got the baseline copies of the bytecode going, we were able to get up to about around 10% slower on some platforms. On some platforms, I think it's even like 1% to 2% slower, which is really kind of amazing. So we've done a lot of work that has kind of advanced both teams. So one thing that is really expensive in the free threaded builds is reference counting. As you saw, there's a lot more stuff going on there. And so for that, we have stack refs, but it's something that lets us say, hey, I have a borrowed reference here, or hey, I have an owned reference here. And so we can just, like if we're loading a local that we know is never replaced, for example, inside of a function, we can just pull a borrowed reference from it, and that state needs to be tracked through the interpreter for when that local is no longer on the stack. And that's something that has improved both builds. The really cool thing about that is it's kind of, instead of just having PyObject stars everywhere in the interpreter loop, we're starting to have a little bit more structure, and that structure might bring about the opportunity to have things like tag pointers, which are just unboxed integers inside of the interpreter loop. One fun thing about this is that naming is hard. There's a lot of contention sometimes. But we eventually come to agreement.
All right. Cool. So that concludes the most technical part of the talk about what we've built and how we've made these things work together. Now I'm going to put my manager hat on and talk about like how we get that to actually work in the real world and actually get built and not have it be a pile of constant arguments all the time. The main thing is we all just kind of agree that even when there is technical conflict, like this thing that you're planning to do is going to make it harder for me to do this thing I'm planning to do, that does not mean that we have conflicting goals. Our goals are actually for all of us to be successful and have Python get faster in all directions at once. So just kind of constantly enforcing that, which I think everyone does believe on both teams, is really, really helpful. Also, you kind of have to agree on what you are doing and agree on a sense of truth as best you can. So there's a standard set of benchmarks that have existed for quite a while. I think they started with Unlaid and Swallow, but they have sort of become a community resource and changed a lot over time. There's also another set that began with Piston called Python macro benchmarks. We use both of these. I talked a lot about this in my talk at PyCon last year. A lot of the problems with them, like they're not all perfect. They don't all represent Python in the real world, and some of them have a lot of noise, and so there's ongoing work to make all of that better. But I think the biggest challenge that we have sort of at this juncture is all of the benchmarks in this suite, at least, are all single-threaded, and we do want to start also measuring what happens when you have concurrency, which is kind of a whole different set of issues. You not only want to measure wall clock when you're using all your cores at a time, you want to be measuring the scalability of different benchmarks and approaches. Like, as I add more cores to this, does it continue to increase in throughput, or is there some weird cliffs? So whereas single-threaded is fairly straightforward in that you're running them and you get a single number, which is generally wall clock time, scalability can have all these weird different shapes and stuff, so it's a little more complicated. But I'd say this is the biggest thing we should be working on, and also something, if you're interested in contributing and you're interested in trying out the free-threaded builds, it would be great to have benchmarks related to that submitted that match your own workloads for what you're doing. Oh yeah, and I already mentioned the sort of signal-to-noise ratio problem remains a problem that is ongoing. And then another interesting thing that I sort of wasn't aware of because I wasn't working at a big tech company at the time is around 2019, all of the big tech companies were maintaining their own mutually incompatible internal forks of Python because they all had their own performance issues that were kind of specific to what they were trying to do. And it is often much easier to fix those issues for yourself than to push upstream and try and find solutions that work for everyone or that are super general. So it's completely reasonable that we're in this state, but it is also maybe not the best long-term approach because it means Python, both externally because the broader Python community doesn't always get to benefit from these things, but even internally, if you are not tracking upstream CPython, every time there's a new CPython release, there's a whole bunch of work that you have to do to bring your fork up. And so I definitely think both Microsoft and Meta were trying to solve this problem and work much more in the upstream. It is a slower way to work, but I would argue the much better long-term bet. There's a really good book called Working in Public from Nadia Egbal that sort of explores a bunch of different ways of working together in the open and describes which ones work for various different things. I highly recommend it if you find yourself managing this kind of work. A very important part, and it seems obvious, is that we have shared weekly meetings. We're still asynchronous. We're all around the world. We primarily work on GitHub and in Python Discourse and Discord, but those things kind of only get you so far until you have to these are the things we're having trouble pushing through, and nothing really beats synchronous communication to work through those things. And also just for general constant awareness of what each team is doing is super helpful so that there's no surprises. I've been working for 8 weeks on this thing and now you're telling me it's going to conflict with your thing. We try not to have long stretches of surprises like that. And then lastly, all of that sort of works in the consensus-driven development that is required to work on core CPython. We are two companies, we have things we want, but we can't just railroad that into the broader CPython community. We have to work with them, write PEPs, come to the language summit, convince and find that consensus and change our roadmaps to fit in with others and stuff all the time. And like I say, that is the hard work, but I think ultimately the right thing going forward. So that is everything. We're a little bit under time, but we're going to take the questions in the hall if you have any questions. And thank you very much for coming today.